There are two ways of spreading light. One is to be the candle and the other is to be the mirror that reflects it. I am Anita from Silver Hills Public School. Today I am going to discuss with you a subject which is the most intriguing and fascinating of all the subjects possible. Today we can discuss a 10th standard physics portion that happens to be light. Light shows many properties, and we have learnt in the lower classes many important properties that are exhibited by light are reflection, refraction, dispersion, total internal reflection, scattering. Each phenomena that you see around you is actually a game or a play of light. Light is such an important part of our life. Here, very specifically, I am going to discuss about the images formed by spherical mirrors. Before we start with the image formation of spherical mirrors, there are certain parameters that is essentially to be understood here. So I start off with the parameters of spherical mirrors. How is a mirror actually made? A mirror can be easily made with the help of a hollow glass sphere. What I do is I am going to paint the outer side of this hollow glass sphere with a silver coating, and I am going to just chip a small piece of that sphere. Obviously the sphere will have its own center, the sphere will have its own radius, right? As I chip it off, what do I get? I get a small bowl. Right? When I turn it onto my face, it looks like a concave mirror. Let us see with a diagram here. So here is my hollow glass sphere, which I happen to paint with a silver color at the outer side. And as I chip off this part off, as such it's hollow inside, right? As I chip off this part off from here, I get this small, beautiful spherical mirror, which happens to be a concave mirror because it's bulging inside. Right. So what are the parameters that defines a spherical mirror? So obviously we have understood that a concave mirror is a part of a whole sphere of which a small piece I have pulled it out or chipped it out. Right. So the center of the sphere is actually the point which is the most symmetrical center of this whole hollow sphere, right? So when I chip it off, I take a piece of it. This point of the mirror is going to be called as the center of curvature. Now, the symmetrical center part of the mirror, the absolute symmetrical center part of the mirror is going to be called as the pole of the mirror. A line that passes through the center of curvature and the pole of the mirror is called as the principal axis. On the principal axis, there is a very important point again lying that's called as the principal focus. So basically, one spherical mirror is different from the other in terms of these parameters. Specifically, the center of curvature differs as my diameter of my sphere becomes bigger. Obviously, my center of curvature point is also going to be bigger. But the point pole, the center of the mirror, is the same for all kinds of mirror that we are talking about. So one mirror is different from other in terms of its radius of curvature, and that happens to be the distance between the pole and the center of curvature. And we can just imagine that our principal axis is a reference line that actually passes through the center of curvature and the pole. Now, I am giving you a cross-sectional view of how the mirror is going to be after I have sliced it off. Okay, so as I have told you, my reference point is my principal axis that goes straight. The center point is the pole, right? Center point of my spherical mirror. Okay, the center point of the reflecting side of the mirror is going to be your pole. And C over here is my center of curvature. The distance between the pole and the center of curvature, I told you, it is the radius of curvature. Here, at the absolute midpoint of your pole and center of curvature lies the focus. The focus is half of the radius of curvature. So obviously, if my radius of curvature is different for the spherical mirrors, so is my focal length going to be. Right. So what are the parameters that defines one spherical mirror with respect to other are the focus, the point of focus in other words, the center of curvature, hence the radius of curvature, and the next one is the aperture. The aperture can be taken as the reflecting side or reflecting part of a mirror. The entire reflecting part of a mirror is going to be called as the aperture. That aperture can vary from mirror to mirror. Right. Now, next what we can talk about is the focus point for the two types of mirrors that we know, that is a concave mirror and a convex mirror, differs in terms of their positioning. Now, for a concave mirror, if the parallel rays of light are coming and falling on it, after reflection, it converges to a point ahead of the mirror called as the focus. But just give it a small comparison to the other figure that I am having there. I am having a convex mirror. Okay. So, in that case, see the same parallel rays of light I am allowing it to fall on it. But then where is these dotted lines coming from? These are the imaginary lines. It appears as if these parallel rays of light after reflection are actually coming from the focus. So, this point of focus is actually lying inside the mirror or within the mirror, or we can also call it as behind the mirror. Check it once again. In this case, the concave mirror, you are having the focal point lying ahead of the mirror. Whereas in a convex mirror, you find that the focal point is lying within the mirror, inside the mirror. And it appears as if the parallel rays of light after reflection were coming from the focus. Next, center of curvature. The point in the center of the sphere of which a mirror becomes a part. Radius of curvature. The linear distance between the pole and the center of curvature is called as the radius of curvature. Principal axis. The imaginary line that passes through the pole and the center of curvature of a spherical mirror is the principal axis. The pole, the midpoint of the spherical mirror is called as the pole. Aperture. An aperture of a mirror is a point from which the reflection of light actually happens. It also gives the size of the mirror. The principal focus, very important point for a spherical mirror. Principal focus of a spherical mirror is a point on the principal axis of the spherical mirror at which the light rays which are parallel to the principal axis essentially converge or diverge after reflection. And we know that convergence happens for a concave mirror and divergence happens for a convex mirror. Next, focal length. The distance between the pole and the principal focus of a spherical mirror is called the focal length of the mirror. And mathematically, as I told you, it is half of the radius of curvature. So, that is all about the parameters of spherical mirrors. So, there are 5 parameters that you should keep in your mind. First happens to be the point called as the center of curvature, hence the radius of curvature, pole, focal length, and last is the principal axis. These 5 parameters, if you are able to define well, you can draw all the diagrams for a concave and a convex mirror. Knowing the parameters of spherical mirror, let us discuss the rules that govern the image formation in spherical mirrors. We can start off with the concave mirror. The first rule, a ray of light parallel to the principal axis after reflection passes through the principal focus of a concave mirror. Next is rule number 2. A ray of light passing through the center of curvature of a concave mirror is reflected along the same path. You could see the arrowheads. This is actually like a ray of light is passing through the normal. So, the angle of incidence is 0, the angle of reflection also becomes 0, and that is what the principle of this rule is actually. Third rule, a ray of light passing through the principal focus of a concave mirror after reflection becomes parallel to the principal axis. And the last rule is actually very pictorically explaining us the laws of reflection. It is the incident ray, the reflected ray and the normal all are lying on the same plane, and the angle of incidence is equal to my angle of reflection. So, what is the rule all about? A ray of light incident obliquely towards the principal axis and to the pole of a concave mirror. After reflection, it makes the same angle with the principal axis. Okay, these are the 4 rules which are very much essential to understand the image formation in concave mirrors. Now let us see what are the rules, the same rules, how it is going to be applied for a convex mirror. So next lies the topic, rules governing the image formation in spherical mirror, convex mirror. First rule, a ray of light parallel to the principal axis of a convex mirror after reflection, it appears to be coming from the focus. The dotted lines are actually our imaginary lines. It is imagined as if the ray of light is coming from the focus. Check with the second rule, which is almost close to our rule for the concave mirror. A ray of light going towards the center of curvature after reflection from the convex mirror is retracing the same path. Here is rule number 3. A ray of light moving towards the principal focus of a convex mirror becomes parallel to the principal axis after reflection. Check the last rule. A ray of light which is incident obliquely to the principal axis and it's moving towards the pole of a convex mirror, after reflection it makes the same angle with the principal axis. So these are the 4 rules that are required for image formation in a convex mirror. Knowing the rules governing the image formation for spherical mirrors, we can draw all the 8 diagrams for the concave and the convex mirrors put together. Again, if you recapitulate on what we have learned in the last topic, the first rule was a ray of light that comes parallel to the principal axis after reflection passes through the focus. A ray of light that passes through the center of curvature of a concave mirror after reflection retraces the same path. A ray of light that is travelling through the focus of a concave mirror, after reflection it becomes parallel to the principal axis. A ray of light that travels obliquely towards the principal axis and to the pole of a concave mirror, after reflection it makes the same angle with the principal axis. So knowing these 4 rules, any 2 rules are enough for you to draw the diagrams, the ray diagrams for a concave mirror. We can start off with the concave mirror. So obviously knowing about the parameters, that was the different positions that we have spoken about and the different features of a mirror, Importantly, we should come to know the focus, the radius of curvature, center of curvature, and beyond are the positions at which we are going to keep our objects. And the first diagram that you could see over here is when the object is kept much beyond the center of curvature. The object is placed at infinity. With respect to the size of a spherical mirror, the distance infinity can be defined because the size of the mirror will be very small. A close distance compared to that can be taken as a point of infinity here. So, these parallel rays of light are actually drawn as rays of light coming from infinity. These rays of light, after hitting reflecting surface, as the rule says, it should all pass through the focus. In this case, I have selected two rays of light, but they are using the same rule over here. The rule happens to be the parallel rays of light after reflection passes through the focus for a concave mirror. So, both these rays of light that I have selected over here are following the same rule. And what do we see? These two rays of light are meeting at a point called as our focus, right? So, the object is lying at infinity, the image will be created at the focus. You could see that the image is very, very small and it is called as a highly diminished image, or it is just called as a point image. The image is actually formed in front of the mirror and it can be obtained on a screen. Hence, the image so formed over here is a real image. So, what are the features of this particular condition where the object is placed at infinity? First of all, image will be created at focus. Second, image is point size. Third one, image is real and it is inverted because it can be obtained on a screen. Next, if I bring that object little more closer to the mirror or little more closer to my center of curvature. So, my center of curvature point lies here and I have kept my object a bit far away from the center of curvature. Again, I am going to use two rules over here. So, what I do is, I have my first rule here in place, the parallel ray of light after reflection passes through the focus. A ray of light that passes through the center of curvature after reflection retraces the same path. Now, these two rays of light after reflection, where they meet, at that point you will get your image. And this is exactly the point at which they crisscross, right? So, this is the point at which my image is created. Now, check on the object and the image. My object is standing upright. What about my image? My image is inverted. And whenever we are going to have an inverted image, we are going to have a real image, right? Because it can be obtained on a screen. Now, what is the other feature that you could see? Very clearly, when I compare the size of the object and the image, my object is bigger, my image is smaller. So, I can say that the size of my image is diminished, right? And where is it formed? It's formed between the focus and center of curvature of the concave mirror. Now, let us check on the next diagram. Here, I bring my object now close to my mirror. I am going to keep it at the center of curvature. And here I am going to use the first and the third rule. A parallel ray of light after reflection passes through the focus. A ray of light passing through the focus after reflection becomes parallel to the principal axis. Now, check where are they meeting? These two reflected rays of light, where are they meeting? They are meeting at this point. And just see, just on top of it lies my object. And this happens only at this position when the object is placed at the center of curvature. Now, have a good look at the size of the object and the image. The size of the object and the image are the same. And the image so created can be obtained on a screen, hence it's a real one. And while drawing this diagram, there are certain tricks to do that. Quite often, when you're trying to get your image in place, it's going to be a perfect mismatch. It will never fall on to this position here. This happens because if your distance from the pole to the focus and from the focus to the center of curvature, if they are not equal, you will never get a perfect diagram. So whenever you are trying to draw this diagram, make sure that these two distances are equal. In that case, at first shot, you will be able to get your diagram perfectly in place. Now look at the next figure, where I have kept my object now. I have pushed it inside the center of curvature. Like object is lying between the focus and the center of curvature. Again, we can use the first and the third rule. I have my parallel ray of light, reflected, passes through the focus. Ray of light passing through the focus after reflection becomes parallel to the principal axis. They meet at a point beyond the center of curvature. Now have a look at the image again. My image over here, not my image, my object's image is going to be getting bigger now. And real also, because it's inverted, can be created on a screen. Next one. Can you guess what rules did I use over here? Parallel rays of light after reflection passes through the focus. A ray of light that is in the line of my center of curvature will be reflected in the same direction. Very clearly, I have kept my object at the focus. When my object is kept at the focus, I am getting the reflected rays which are parallel to each other. And these two parallel rays of light obviously are going to travel some distance till infinity to come together. At the point of infinity, I will be able to create an image which will be very, very enlarged. So obviously, isn't it the opposite of what you see in the first diagram? When the object was there at infinity, where was your image created? At the focus. Here it is, the object is at the focus. Where is the image getting created? Image is getting created at infinity. Obviously, the ray of light is, these two rays of light are shown below the principal axis. The image so created over here will be real and highly magnified. The last one is a bit of a tricky one which requires some amount of thinking. Though we are yet using the same rules, the fourth set of rules are what we are again going to be, of that any two we are going to be using here. And I try to keep it pretty simple over here. The object now is lying between the pole and the focus. I again use two rules here. A ray of light parallel to the principal axis after reflection passes through the focus. That happens to be one of my favorite rules also, because I use it everywhere when it is spherical mirrors in consideration. The ray of light which is in the line of the center of curvature after reflection is going to be going straight through the same path. Right. Now, how is the image going to be created? When I have a nice look at it, the reflected rays of light are like diverging away. They are moving apart, right? So I tried a trick. I tried to put some dotted lines and stretch these two lines towards the other side of my mirror. And I found that they were meeting. And why do I put these dotted lines over there? They are assumed to be present there. We are imagining that they are present over there. And at this point where these two rays of light are imagined to meet, we are going to create an image. And this image, as you look, is standing upright. And this image is getting created inside the mirror or behind the mirror. This is the only case in a concave mirror where you get a virtual image. And the image so obtained is also enlarged, or we can say magnified. So when the object is placed between the pole and the focus of a concave mirror, that is the only position in which you are able to get a virtual, upright or erect image. Now, if I put the whole positions in terms of a chart, this is something that I am able to get. So, positions of the object at infinity, the image was created at the focus. The size of the image was highly diminished or point size, and the nature of the image was real and inverted. What I get next is I keep the object beyond C. Just beyond C is also enough. Beyond C, the image was created between the focus and the center of curvature. The image was diminished, again real and inverted. At C is a unique case. At C, that means what? My object and the image are created at the same point. The only thing is that my object is upright, my image is inverted, hence my image is real. Size is same size. Next, when I keep the object between the center of curvature and the focus, I get my image beyond C. It is enlarged. Now it starts becoming bigger. The image starts becoming bigger than that of the object. Again, real and inverted. At focus, the image will be at infinity, highly enlarged, yet real and inverted. Check the last one. Between the pole and the focus, if I keep my object, the image will be formed behind the mirror, it will be enlarged or magnified, and it will be erect and virtual. That's all about the image formed by a concave mirror. Now let us check on how are the images formed for a convex mirror. The image is formed by spherical mirror, convex mirror. I have this first diagram where my object is lying at infinity, and whenever parallel lines are in reference, it has something to do with infinity. Here when I show the arrowheads over here coming in, this indicates that the parallel rays of light are coming from an object lying at infinity. If the arrowhead were outward, it indicates that these rays of light are approaching infinity. So I use my first rule in both the rays over here. A parallel ray of light after reflection appears to be coming from the focus. So when I use two rays of light, I find that these two rays of light are actually seen to diverge from a point called as focus. So you are going to get a virtual image because this image is getting created behind the mirror, right? So I am going to get a virtual image but point size image inside the mirror. Next one. Only one case is actually possible for a convex mirror. You can always keep the object in front of the mirror. There is never a possibility of keeping an object within the focus or at the center of curvature and all that. So again, I went and kept an object in front of a convex mirror. I used my rules. A parallel ray of light after reflection appears to be coming from the focus. A ray of light that is moving towards the center of curvature appears as if it is getting reflected from the same position. And where are they meeting? They are meeting inside the mirror, behind the mirror. Okay, and check the image. A tiny looking image is there which stands upright. So the image is virtual and the size of the image is smaller or diminished than that of the object. And if you check the chart, it's even more simple here. Position of the object, it's always in front of the mirror, right? At infinity, image will be at the focus. It's highly diminished. I'll always get a virtual and erect image. Next, if I keep it between infinity and pole of the mirror, it can be any point. Between pole and focus, behind the mirror, diminished, and the nature is virtual and erect. This is all about the image formation in spherical mirrors. We have discussed about the concave and the convex mirror. I thoroughly enjoyed being with you, and I hope it's going to help you in preparing for your board exams too. Thanks a lot. Thanks for being there.